This video is going to cover torsional stress. Torsional stress is tau, which is a type of shear stress. Because it is actually changing the cross-section, it is twisting it. Now what we're going to be focusing on is circular cross-sections to make it simpler. However, because it is changing the shape of the cross-section, that's technically a type of shearing stress. The difference is that it's not using the value for shear force in the equation. Instead, we're going to be using torque, which again is torsion. So that's a moment, but it's a twisting moment. And then we multiply by rho and divide by J. So T, again, torsion. And the units for that are going to be pound inches, though nobody's going to talk about it in terms of pound inches because again that's weird, but we're going to say it's pound inches for the sake of this just so that we can keep our units straight, or Newton millimeters if we're in SI. Next we have rho, and rho is again the distance to the center of the cross section. Usually it's anywhere from 0 to R. So if you have a circle, we're looking at from the center out to, say, spot A over here on the edge, that's rho, which again is the radius. If for some reason you wanted to find it, I don't know, halfway over, that would also be rho. If you had a tube and you wanted to find it at the inside of the tube, well then that's rho. So again, it is literally just the distance to the center of the cross section from, of course, your point. And J, and since it is distance, remember that distance is either in inches or millimeters. And lastly, J is polar moment of inertia. So polar moment of inertia is going to have units of inches to the fourth or millimeters to the fourth. And polar moment of inertia has its own fun equation. Now, if you're looking at all of these units, you have pound inches times inches divided by inches to the fourth. You're going to have our stress in PSI. Same thing for SI units. It's going to be newtons per millimeter squared, which, by the way, is a megapascal. So what's J? J is polar moment of inertia, and that has its own equation, which is pi over 2 times c to the fourth. Now c, strangely enough, they chose the letter c when really they're again talking about the radius. Who would have guessed? And this is what the equation is for a solid cross section. We have a different one if it's a tube. If it's a tube, we have pi over 2 times the outside radius to the fourth minus the inside radius to the fourth. So CO is the outside radius and CI is the inside radius. And again, this is for if it's a tube. Really not complex, just a little bit of plug and chug, just a little bit different from what we've done before. So let's hop into an example. So in this example, I hadn't pre-drawn it this time, but we're going to have a tube and it's going to be fixed. So however you want to draw that lovely picture. We're going to have a force, twisting force, of 95 kilonewton meters. We have an outside diameter of 100 millimeters, and we have a thickness of the wall of 15 millimeters. And what we want to do is we want to find the maximum shear stress. And remember, shear stress is tau, right? That is shear stress. We're not going to be using it with V over A, not that. We're going to be doing shear stress though, but it is due to torsion. And we want to find shear stress at the inner wall. So that's our problem. Let's hop to it. First things first, you know that our equation is tau is equal to T times rho over J. T is torsion given right there, cool. Rho is the outside diameter or the outside radius if we're going all the way to the outside wall for the maximum, or for the inner wall, it's going to be the inside radius. So we technically have those kind of already pre-given, but you know what we don't have? We don't have J. So let's find J. Again, we're a tube, so a tube is going to be pi over 2 times, again, outside radius. And again, our radius, we have diameter. So if our diameter is 100 millimeters, divided by 2, magically that's now radius. Put that to the fourth and then minus off your inside one, but our inside one's a little bit different. Our inside one is going to be whatever our outside one is, minus that thickness. So a little bit longer, but that's J. So now let's put J in a new color. Let's put him in red so we can follow him. So J is going to be equal to 7.46 times 10 to the 6 millimeters to the fourth. So if we want to find maximum shear stress, effectively what's going on, if you look at that equation, is that the farther you are out from the center, the higher the shear stress is going to be. If you're at the center, if you're looking at the center, then rho is equal to 0, and thus stress is also equal to 0. So what's really happening is as we're twisting it around, we're going to be having an increase here of stress. So that's kind of how it's twisting around. So if I want to find maximum, if I want tau max, my maximum shear stress, that is when rho is rho max, which is, in this case, the outside radius, because we're a tube. All right, so the maximum shear stress for our system is T. T is 95 kilonewton meters times rho, and remember we said that's outside radius. So outside radius, we have the diameter of 100 millimeters divided by 2. There's our radius. Divided by J. And J we have as 7.46 times 10 to the 6 millimeters to the fourth. See anything wrong with this so far? It's units. Yep, we've got millimeters and millimeters to the fourth, and then we've got kilonewtons and meters. Weird. Let's go ahead and turn everything into millimeters. So we have 1,000 millimeters and 1 meter. Let's cancel out some of this garbage. So goodbye meters, goodbye meters. Now we're going to have millimeters times millimeters, so millimeters squared divided by millimeters to the fourth. Those are all going to work out. So we're going to be left with, for our maximum, kilonewtons per millimeter squared. That's gigapascals technically. And what we're going to get is 0.637 gigapascals, or again, kilonewtons per millimeter squared. Now it's kind of awkward to talk about it in terms of kilonewtons per millimeter squared if you have not even a whole number. So this is really 637 newtons per millimeter squared, which again is megapascals. So that's our maximum value for our shear stress. And of course, that is occurring at the edge. So along the edge is where a maximum is, and that maximum value is 637 megapascals. So that's one of the things that we wanted to find. The next thing we want to find is the shear stress at the inner wall. So this time, I want to find what's the shear stress along the inside. So it's effectively the exact same thing, except now we're just imagine that inner ring. So the only thing that's changing is rho. Rho is going to change. So at the inner wall, our rho that we're going to use for our equation is the inside radius. Again, the inside radius, we didn't have it given to us, but it is going to be the outside radius, which the outside radius was 100 millimeters divided by 2, right? That's the outside radius, but then minus the 15 millimeter thickness. Should probably be consistent with that parenthesis. And when you do this, you have 50 minus 15. Our inner radius is 35 millimeters. So if we want to find shear stress for the inner wall, that's going to be, we have our torque, and our torque again was 95 kilonewton meters. So 95 kilonewton meters times that inside radius we just found 35 millimeters divided by J, and J didn't change. J is still the same, so that's 7.46 times 10 to the 6 millimeters to the 4th. Again, we have meters and millimeters, so we need to change somebody, so let's change this to 1,000 millimeters in 1 meter. Cross out our units, make sure they're going away. Goodbye meters, goodbye meters. We're going to be left with kilonewtons per millimeter squared. So our inner value for shear stress is going to be 0.446 kilonewtons per millimeter squared. However, kind of awkward to talk about that. Might as well just change it to 446 newtons per millimeter squared, which is a megapascal. So it's really not complex. This torsional stress, again, it's just kind of weird that we talk about it as it's a shear, because it technically is a shear, but it's actually a pretty simplistic equation.